Thank you for waiting. Now we would like to begin Dr. Morten MELDAL's lecture. Today, Dr. MELDAL will be lecturing online. Dr. Konosuke Oisaki from National Institute of Advanced Industrial Science and Technology will be the moderator of this session. Please welcome Dr. Oisaki.
Okay, good evening, everybody. My name is Konosuke Oisaki from AISD in Tsukuba City, and I am the moderator of this session. It's my great honor to introduce Professor Morten MELDAL to you all. He's a distinguished alumni of the Technical University of Denmark, where Professor MELDAL obtained his PhD degrees in organic chemistry in 1983. And following his graduation, he did a postdoc in the at the University of Cambridge. And currently, he holds a prestigious position at the University of Copenhagen, where he also leads the Center for the Evolutionary Chemical Biology. Professor MELDAL's research interests lie in the field of the synthetic organic chemistry mainly, and particularly related to the peptide chemistry and combinatorial chemistry. And this research topic is very, very important for the identification of the new drug seed molecules. And one of his establishment of kappa-catalyzed azide-alkene cycloaddition reaction that is also known as a room temperature quick reaction is very, very useful to nowadays for developing the novel drug modalities. And that can also be used for the connecting the various kind of molecules, such as biomolecules and small molecules, of course, and other material stuffs. And that is recognized as a landmark achievement in the field of the bioorthogonal chemistry. And because of his remarkable work, he got numerous awards. And here, I'd like to show pick up the only one prize in chemistry. As you all know, that honor he shared with the Nobel Prize in chemistry with the co-recipient, Karen Bertozzi and Barry Sharpless. And actually, I had a chance to attend the Australian Chemistry Symposium last year, and I listened to the MELDAL lecture there. And I heard that a very interesting story about finding the kappa-catalyzed quick chemistry reaction that is serendipitously found. That inspired me a lot. That is based on a lot of the experiments and synthetic chemistry thought. So that I am confident that Professor MELDAL's lecture will inspire all of you all. So please start the lecture, Professor MELDAL.
Thank you very much, Dr. Oisaki, and thank you very much for inviting me to come here to the HOPE conference and talk about not only the click chemistry, but also entertaining a little bit with what it is to get a Nobel Prize, and also sort of giving a perspective on what I think is important. So molecular click adventures, a leap from the shoulder of giants, is of course something that says that we are not doing things in isolation. We all work on the basis of great results from other scientists. And I would like to immediately thank my supervisor, Klaus Bock, and also people like Bob Shepard, who I worked with in Cambridge, and Hysken, who was a forerunner on the cycloaddition reactions that I'm going to talk about today. When you get a Nobel Prize, you also get the opportunity to say something important. And what I think is really important is to realize that everything around us everything within us is chemistry. It's chemistry when we feel pain. It's chemistry when we are hungry, when we are tired. That's all peptides that interact with receptors and give us these kind of feelings. So if you are feeling good, it's probably because you have a dopamine release or something like that. And everything is controlled by chemical reactions in the world around us. Therefore, I think it's very important that we get young people to study chemistry already from the first grade. So if chemistry is really everything, why don't we teach that from the very beginning? And that would then also allow me to talk about research with no constraints. I think that we cannot have research constrained by people who have no idea of what the research is all about. So therefore, I think funding by performance is a must in research. If you actually perform well the last 3-4 years, why don't we just get a bag of money for the research for the next 4 or 5 years? Because the impact is when you do something really spectacular and unexpected. If we look at the Nobel Prize is today often shared, and I shared this Nobel Prize with Barry Sharpless, a very good colleague of mine in San Diego, and Carolyn Bertozzi, who I've known since she was a PhD student. I discussed all her visions with her at that time in a meeting in US. And we have always been very good friends. We have never collaborated, but been very good friends. So where does it all come from? Why do you get inspired to do chemistry? There can be many different reasons. Either you are interested in explosives or drug development or something like that. But in my case, it actually came from my experience at my grandfather's farm on a small island called Bornholm in Denmark. This is the farm that you are looking at. This is a meadow, and behind you see the trees and the forest. Up in the corner, you see me at the age of 10, I think. And this is when you go inside the forest. And it always occurred to me that nature was amazingly beautiful. And everything in nature actually fits together. There's a role for every single thing in this image of nature. And my thought was, what is it that creates this harmony and this collaboration, this synergy in nature? And the only answer I could come up with was that this must be residing in the way that the molecules interact, the way that the chemistry is inside these living organisms. It must be encoded in some way. And therefore, I started actually my interest for chemistry with this, and also from building crystals and from making fireworks later on. That was really exciting. But what do I look for today in a young person who comes to me and wants to work in the lab? Well, I look for many other things than the factual knowledge. Factual knowledge is important. It is training your brain if you get factual knowledge. But there's a lot of other abilities that are very, very important for me for working properly in the lab. The first thing is intuition. You need to have intuition in order to combine and find what way to go based on the observations in the experiments. Your imaginations, your ability to form pictures in your mind, abstract or real pictures in your mind about what is going to go on in the next step is also very important. Are you able to associate the different knowledges you have with the observations that you do? Can you combine? Can you be creative and make new associations based on the old ones that you have already? Are you able to collaborate? And most importantly, do you have courage? Do you have courage to contradict your supervisor and tell him that he's completely wrong and that your idea should be actually tested in the lab? Because this is where the novelty comes up, is when you have this kind of ping pong between the supervisor and yourself. and that you are actually allowed to do these things depend on your courage to tell what you want to do. Of course, computational skills is a must today, and then perseverance. Are you able to, do you have the stamina to actually pursue your your experiments to the end? But the road to success in science is never straight. Almost always science projects, if they are challenging, will fail initially. So the idea that your PI might have gotten behind the office desk is not always watertight, and it can often fail. And then you just have to look for the opportunities in your experiments and then go for the best opportunities. Again, that's where your courage comes into play. So there are many factors that determine your path, and you will fail and you have to rise again. So that's a perseverance. Time is very precious when you do these kind of studies. So you have to use your time optimally, and you have to get out of your comfort zone. If there's something you don't know, don't let it stand on the sideline. Just go into it, push it. You have to change your field occasionally, because if you have several fields of expertise, you have a higher chance of hitting something really novel in between the fields. So in the periphery of what you know in two different areas is where the novelty will come. That actually means that your life is one long study. You can never relax. It just continues forever. So as a young scientist, I started here at Carlsberg Laboratory. They were working with biochemistry, and you see a lot of enzymes there. So we wanted to be able to study biomolecules and organic chemistry and the interface between these when I started at Carlsberg Laboratory. So we developed these polymers that you see here, the polymer up here, and we tried to do a lot of different organic reactions on these resins. And since it's solid phase chemistry, it was very important that we were able to carry out these reactions in a pure and quantitative manner. And all of these reactions have actually been developed to give us single products on the solid support. And the first one up here is the Diels-Alder reaction. The Diels-Alder reaction is sort of orthogonal to nucleophilic electrophilic reactions. It's an electrocyclic reaction. And we would like to use that and introduce it into the center of peptides, and then modify the peptides, for example, with long fatty chains that would increase the lifetime in circulation. And we tried to do this reaction with the isolation of copper acetylides on the solid support with acetoacid chlorides, and it never succeeded. We found out by studying all the spectra that this was because we had formation of the triazole. So the QARC reaction was sort of a serendipitous discovery. Once we had seen that this worked, and it worked quantitatively, we then focused entirely on that reaction for a while. But the fundamental research that, or the fundamental technology that we developed was these resins, polar resins with PEC, a lot of PEC, and they are actually useful both in unpolar solvents and in enzyme buffers. And for this reason, we could use all of these reactions here to make enzyme inhibitors, and we studied subtilisin, trypsin, all sorts of proteases, also glycosyltransferases on solid support. This was all made feasible by the Danish National Research Foundation and the Spock Center, which we created at the Carlsberg Laboratory. So is such a center of excellence is very important, and I had a question during our question session about what would you do in the developing world if we want to have a sort of, if we should live up to the situation that you have in the developed world. And it's very important to have centers of excellence that can attract the best talents around. So you have to develop a strong idea with a challenging which is a challenging and current scientific area, identify real problems and solve these challenges, suggest feasible solution to the problems. And if you do that and you submit such an application, there's a good chance that it can be honored from one of the funding agencies, either in your own country or abroad. So in my case, I had to select and align the host institution with the purpose and the process of the center. This was quite important for us to succeed because what goes on in that center was completely different from my new research idea. So we had to establish a lot of new infrastructure, alliances, and collaborations. Then we composed the application with a strong component on fundamental research. So not so much application, actually. Although application is important, the really new breakthroughs comes from fundamental research, and I'll come back to that later. We had a close fit between the core and the hiring plan, and a strong component of education as well. So who can say no to such a program? So we got it from the Danish National Research Foundation, and we could establish a critical mass group with a very good infrastructure for studying biomolecules. And I cannot emphasize enough what it means to have the instruments that are necessary to actually carry out the research that you want to do. You should listen to your co-workers in that infrastructure build-up. So we established a multidisciplinary center with all things from physical chemistry to biology, with a very diverse group of researchers, and we hired worldwide. We had a group of 25 people at the peak, and this was working extremely well. We had a very short annual meeting with the funding agency, and they enforced a very good dialogue and a positive forward-looking, attitude. So we had very limited administration in this. And the most important thing with this contract with the funding agency was that we had to implement at least 30% entirely novel plans every year. So we had to come up with new ideas every single year. We were not following one closed research plan from start to end. And that actually allowed us to follow up on the observations that we had with the quick reaction. So the co-worker profile was that we had surprisingly talented people applying for the positions there. And we had a very nice WIP international network from Klaus Bock and myself, the two applicants for this application. And such centers are really essential for technological development and for maintaining the expertise in the country that you are in. So this is extremely important. So what should you study then? Well, I think that one thing could be the green agenda, which is very in at the moment. Here is a material that we make from barley and soya oil. This is just a very strong material. Barley straw and soya oil form this in a polymerization reaction, and it's almost like the plastics that we are using today. So this can replace fossil plastics, and maybe we can even make packaging with cellulose, new textile materials, and green polymers. We also need better production processes with new kind of catalysts that can actually do the reactions that we do now at great suffering for the environment in water with much less efforts. So development of new catalysts that can do actually the reactions that we want to do. And in particular in the energy sector, where solar technologies, degradable wings for windmills, you have transition to hydrogen or hydrogen sources, and we should try to make this access very global, because the environmental crisis or the climate crisis is harming everyone on the planet. We also need increased and improved foods So that's another area where you can actually do some really good research. New plants with the bigger roots, how can we process things that are available in nature so that they become edible, so on. Textiles, using bamboo instead of cotton, and so on. And finally, transport. Transport is a very important area because transport is responsible for a lot of the carbon dioxide that we have, carbon dioxide emission that we have. So these are areas that are very good for applying, but there are also the medicinal areas, like showing this molecule here. This is actually today one of the foundations of the Danish economy. This is the obesity medicine that Novo Nordisk is selling worldwide. And it really provides a lot of money for research in Denmark. So with all this in mind, here's the technology platform I developed at Carlsberg Laboratory. We started out with the combinatorial chemistry, and this was on polymer particles that we synthesized ourselves with the particular properties of being both compatible with polar conditions, so we could screen, and also with unpolar conditions, so we can synthesize. This can then be screened. For example, here you can see some blue active beads in a large background of inactive beads. We isolate those and find out what the structure on these beads are. We can collect those automatically after the analysis and resynthesis. We can inject it into a mouse foot or a mouse tail and see the inflammation that is in this foot patch here. We can also use the beads as substrates for growing cells in a monolayer. So the cells here will act as a detector of interaction with molecules on the beads. So we synthesized combinatorially a lot of peptides and isolated this adhesion peptide that allows the cells to grow very strongly on the surface. And then we can actually make an assay where we get fluorescence when we have an interaction that is positive. So here you see a library with one active bead on the background of several inactive beads with the cells that are fluorescent. We isolate those, determine the structure of the inhibitor, and we can do that either by MS or using our encoding technology, which is like a barcode. So we mobilize small microparticles inside the bead, and these microparticles are forming a matrix. We determine this matrix, and that acts as a barcode for identification. So we can use these encoded beads and read every time we do a chemical reaction. And when we have an active bead, we can read the code and see the history of the chemistry. This is our combinatorial technology. It's very simple. It's just 20 columns in a Teflon reactor. We take our beads and divide them out, do a reaction in each of the columns. We mix all the beads and put them back again. And we can do this within a few days. We can make millions of different compounds. Interact them with a biomolecule because we have the polar resins, and we can then isolate the actives and sequence or structure determination. So this is a click reaction. It's a reaction between the A site and an alkyne. And I will come much into detail with that. It is extremely efficient. I've drawn only one copper 1 atom here. Actually, several copper atoms is involved in this reaction, like a cluster of copper atoms in solution. And they recruit both reacting partners and make the reaction feasible at very low concentrations. That is the reason it's become so important in medicinal chemistry, diagnostics, biochemistry, surfaces, materials, and nanochemistry. So this is the alkyne. It's a triple bond, and it has like a lot of electrons around it. So it is a high electron density. It's negatively charged on the surface, and it's looking out for positive charge to neutralize that negative charge. So copper 1 has this particular affinity for alkynes. It's quite strange, but you will find that there is many crystal structures where copper 1 is bound to alkynes. Not only one copper atoms, 2, 3, 4, 5, 6 copper atoms to a single alkyne. Once the copper binds to the electron cloud, this proton down here becomes acidic, and the copper atom takes the place of the proton. That doesn't look so different, and it isn't actually. But as I said, several copper atoms can come and interact with this electron cloud. And when the second copper atoms come in, it actually peels off the electrons just like a can of sardines to get into the goodies, the positive charge on the carbon atoms. So this here is the LUMO, or the empty orbitals with no electrons in them. So these are like balloons without electrons, and they are looking out for electron density. Fortunately, the A side comes by here, and it has a HOMO, or a full electron density cloud, that fits exactly in phase and geometry with the overlap with this empty cloud. So we can actually donate electron density into these empty clouds and get a binding. So initially we form this metal cycle. It loses one copper atom, forming the 5-membered ring. And then the second copper atom, by protonation, is lost. We can also use other electrophiles. And then we get this molecule. And then you can ask yourself, is this fantastic? I would say no. We have just connected this molecule with this molecule. And we can do that in many, many ways. But the thing is, this can be done with completely unprotected residues sitting here and here. So we can use biomolecules of very large sizes to do these kind of reactions. If we look at the general scheme of the click reaction, this is what it looks like. It's exactly what I just explained. There's no difference there. And what we have is actually a lot of crystal structures that illustrate the different steps of this reaction. So here you have the copper at the end of the alkyne and the copper on the side of the alkyne. Here both copper atoms is sitting at the end of the alkyne. And in this last one, you see the triazole with still some copper atoms bound to the triazole. So these are crystal structures. You can also see this kind of catalyst here, where the distance between the copper atoms is maintained at exactly the right distance for coordination as in this central compound. When you do the catalysis without this catalyst, you get this gray line down here for the reaction between phenylacetylene and ethyl propionate. But when you add this catalyst, you get this red curve up here. So this red curve is illustrating how much you can catalyze this reaction by adding a catalyst with the right distance between the copper atoms. Actually, the authors of this paper, they claim that you should not use this kind of catalyst in neat reactions because you might risk an explosion. So we have very, very efficient catalysis, at least 10 to the 7th by calculation. And the reaction is maybe 10 minutes, where without the copper 1, it would take 190 years. So what can we do? Now, this is 3 proteins or peptides, and one is able to kill a cell. That is a molecule that we have actually made, which interact with the XIAP, the inhibitor of apoptosis. This here is can be a monoclonal antibody or some recognition molecule that locate tissue, for example, a cancer cell. And this one down here is one that can enter the cells. If you inject these 3 into a person, nothing happens because they don't reach their targets. But if you can combine them using this click handle, and we can introduce click handles by AMBER stop codon suppression technology into proteins, or we can synthesize peptides with the click handles. When we combine these in a jar of copper 1, they will steer overnight, and we get a single molecule that we can then isolate and use in cancer treatment. It will find a specific cell, it will enter the cell and affect the programmed cell death. And it couldn't do that without the clicking. So this is an archetypal click reaction. It has only one caveat. One way it doesn't fit into the click criteria, because one of the click criteria is that it should be performed under benign conditions in the presence of usual things like water and oxygen and nitrogen and so on. And oxygen has this ability to oxidize copper 1 to copper 2. There's a very low barrier for this oxidation. So all oxygen in the solution will actually end up oxidizing the copper 1 to copper 2, which is completely inefficient in click. So the problem here is not so much the oxidation, because we could reduce back to copper 1, but the formation of these radicals, the oxygen radicals, radical anion and hydroxy radicals that are formed, and then they attack your proteins or your biomolecules. So while this is not a problem with small underivatized molecules, it's a huge problem in peptide and DNA and carbohydrate synthesis. And you can see the effect here on a peptide that we synthesized. You see plus 16, plus 32, plus 48. And each of these peaks are many different compounds with oxidation on different sites of this protein. So be very, very careful with oxygen. Get rid of all oxygen if you do the Keurig reaction, and protect the catalyst with the ligands that sits around the copper 1. Here we are. It's 2022 December, and we are in Stockholm. So this is the first day on the week in Stockholm. You are informed of what is going on during the week. All the Nobel laureates are collected here at the museum, Nobel Museum. And you are getting a very good introduction to the week. Then you have to deliver an item. This is the world's first multiple column synthesizer that I made in the garage of my neighbor. He had a lathe that I could use for that. And I was very interested in trying to make combinatorial chemistry, and this was the way that we could do several reactions simultaneously, mix the resin and put it back into this synthesizer. So there are 20 columns in this one, and that allowed us to do combinatorial libraries as well. So that's in Stockholm, with the publication describing it. And finally, you get to sign here on the top. I have to sign my name on a chair that is in the cafeteria of the Nobel Museum. Very important event, according to the Nobel Committee. And I'm very proud. This is Emmanuel Charpentier, just next to my name. So very nice. These are creatures that you should know. They are the Japanese horseshoe crab, and they are used for harvesting their blood. The blood is quite exceptional. They have an innate immune system that engage foreign organisms with macromolecules and send in toxic compounds into the foreign organism and kills it. So this is the reason probably that it has lived as a species unchanged for 400 million years. It's like a pharmaceutical factory with a lot of different compounds in the innate immune system. And we use that blood for actually detecting if we have a bacterial infection in our blood. So the target placing is almost unchanged through time. That is one of the toxins that is using to kill the bacteria. And I'll go into details with that, because we try to convert this target placing, which has 2 disulfide bonds, into a linear sequence with 2 triazole bridges. So we would like to obtain the same ribbon structure and see if we could have the same toxic effect of this compound. During this study, we actually, by NMR, found out that it forms a dimer, hiding away all the lipophilic residues in the center and having benign arginine residues at the surface. So it's like this cannonball which swims around in the serum. It has all these arginines, so it will search out the bacteria with negative charge on the cell surface. And it will open up and form a pore on the surface. Through this pore, all the interior of the cell can flow out. So we will see the cell perforated and it will eventually die. So that's how these target placings work. And now we ask ourselves, can our triazole compounds do the same thing? And we investigated 4 different bacteria: coli, staphylococcus, salmonella, and bacillus subtilis. And to our pleasure, we saw that the natural compound was actually active in 3 of these organisms, and in the 4th one it was completely inactive. The triazole compounds, on the other hand, was equally active generally, and then they were also active in the one where there was resistance to the natural target placing. So we might say that click is good for antimicrobial peptides if we want to avoid resistance. Here's another way that we can use the click reaction. So it's generally known that if we try to express proteases in, for example, coli, they are very unhappy. They actually die. And the reason they die is because it's a proteolytically active compound. So it will cleave internal proteins in the coli and affect cell death. So when you try to express this, you get a very small amount of protein and then the whole thing dies out. So that's micrograms of protein. We thought that we might actually just cut this in 2 and remove the activity and express these 2 in separate jars. So when we do that, here's the expression, and you see 2 proteins being expressed at very high level. So that's good, and we ask the coli if that's okay, if it's happy, and it says yes, it's very good. So we can make several hundred milligrams of these 2 fragments and combine them in vitro. So we simply combine the 2 residues, and they will actually, under the right condition, fold up and bind with the proximity of the 2 parts that react with the click reaction. And now we ask, is this active on this substrate, just like the natural one? And what you can see is our protease is actually a little bit more active than the natural one. So that was a very good success, and maybe a way to overcome the challenges of natural protease expression. So this is a more scientific slide where we show the same thing. So either these 2 or these 2 were used in AMPA stop codon suppression technology to include them into the protein. And they were sitting up in between the 2 protein fragments. These are the expression parts that we did for 1 and 2 and 3 and 4. 3 and 4 here. And you can see the short bridge was not very efficient in clicking. It didn't give us a quantitative yield of this compound, maybe 30% clicked. But the one with a longer bridge is actually a shorter protein, but with a longer bridge, clicked fantastically, and we got a 100% yield mixing the 2 fragments 1-to-1 and adding the copper 1 conditions. So here we are, and this is a day where you give a lecture for maybe 100 million people. Pretty nervous. Maybe you can't see that, but I was actually quite nervous. And then a great relief when the whole thing was over. So we are very good friends still today. I would like to now switch a little bit. We have looked at natural proteins a lot. And what we see is that natural proteins are pretty large compared to the actual function of the proteins. So this here, this protein here, for example, is papain. And the reaction occur up here. It's a cleavage of a peptide. And for cleaving, for making this work properly, you need all of this protein. And that is pretty strange. And the reason is actually that you have tacticity in natural proteins. tacticity is a compromise with expression of the proteins. It's simply financially not viable to express proteins that is composed of more than 20 amino acids. So financially meaning that all the energy cycles, all the enzymes that have to be produced to do this work, it will be impossible to do with a lot of other amino acids. So the toxicity means that we get alpha helices and we get beta sheets and we get a lot of other secondary structures that have to come together to form a hydrophobic core and a hydrophilic surface and a functional cavity. So maybe we can actually change that if we avoid the toxicity. If we avoid the toxicity, we can actually make the protein fold into much smaller bundles and still have a hydrophobic core and have a hydrophilic surface. So that's what we did. We took a string of L and D amino acids. We folded it up and started to optimize the core and the surface and got these very stable protein folds, which are quite small, like these ones here. And they also can have catalytic residues installed. So this is a new way to make artificial enzymes composed of L and D amino acids. They can be made by synthesis because they are only between 30 and 50 amino acids long. And we can use any kind of amino acids in their composition. We're using this method, which is really just, it's called mutational molecular dynamics. And we're using the program Mo to do that. So we make this random LD sequence. We enter into this cycle where we optimize all the different things that leads to stable structure. And then we introduce the click bridges and the catalytic residues, and then we synthesize and test these compounds in solution. So in this way, we could actually make these compounds. In a week or so, we can design and synthesize one of these compounds. And these are serine proteases. So you can see the active site residues lined up here in these proteases. Then we synthesize them and we test them, and we found some of them have very nice activities. I will focus here on SP1, which is one of our active proteases. This work was done by my current group, which is Mads Ramsik, Rusen, Kjærpik, Sara Mellemgaard, Line Andersen, and David Thesis. If we do a long molecular dynamics on these structures that we have developed, you can see that the protein backbone structure is extremely stable. So if we now, to this stable structure, even add a bridge, it could be a click bridge or disulfide bond bridge, we would get something that was really, really stable. And that's what we did. Here's a disulfide bridge, and here's a click bridge, and the three active site residues are these three. We then looked at the stability, and you can see by the RMDS and also RMSD, and also by the distances between the active site residues, that these folds are really, really stable. We can synthesize them in very good yield, high purity. So this is the crude product of one of the syntheses. And you can see there's essentially one compound and essentially one mass spectrum of this compound. You can also see that this is not a natural peptide. A lot of different things with strange letters are in here. And we will then look at the, once it's synthesized, we will look at the cleavage of substrates. So we make a library of fluorogenic substrates, which has an APZ that is fluorescent, and a quencher, which is nitrotyrosine. And if we have this substrate synthesized in this manner, it's completely dark. There's no fluorescence. When we cleave off the nitrotyrosine, the beads will start to fluoresce. So this is what we did. And we started out using one of the most active proteases available, subtilisine, that is, or 7-ACE, that is used in washing powder. That is a very active protease, and you can see here after 5 minutes after addition, nothing, 10 minutes after addition, nothing. We start seeing something at 30 and 60 minutes. Here you can see a very clear ring of blue around some of the beads. Here you have more rings around the beads, and finally after 24 hours you have a lot of the substrates that have been cleaved. But you can see selectivity after 60 minutes. If we isolate this bead, we'll have a very good substrate for that protease. So this is our SP1 protease. This is a synthetic protease that we made. And you can see we start out with dark beads. We have still dark beads after 2 hours. After 3 hours, we start to see some bright beads. 19 hours, more bright beads. 24 hours, 7 days. But you can see even after 7 days, we have a lot of selectivity in this cleavage. And after 3 months, we have complete cleavage of almost all the beads in the library. So we have now a protease that is synthetic and made by synthesis and click chemistry that is almost as active as the most active proteases used in washing powder today. So we think that is a very good candidate for looking into activity of artificial enzymes. It has the two bridges, one disulfide and one click. There was no room for a click bridge down here, so we have only one click bridge. And then we have 3 active site residues. We have the hydrophobic core and we have the hydrophilic environment of this core, which keeps it into solution. So this protease is actually soluble at 4 to 5 milligrams per milliliter, a very high solubility. We are back in Stockholm in 2022. This is the ceremonial dinner or the ceremony where you get the Nobel Prize. You are allowed to hold the Nobel Prize for a little while, and then they ask you actually to give it back. So you're wondering what is happening. But what is happening is because a lot of the Nobel Prizes are given after 30, 40 years. And many of the Nobel laureates actually lost a little bit in the meantime. So here we are. We have to deliver the Nobel Prize back, and we only get the Nobel Prize on the last day, because otherwise some of us will forget the Nobel Prize in the ceremonial hall when we go home. So this is the last day. I got the Nobel Prize. I'm very happy for that. So now I would like again to shift gears. We have a project called beta bodies. Beta bodies are very small molecules that does the same thing as antibodies. So they interact with a surface. They are created combinatorially, and they can interact very strongly with the protein surface that they are designed to interact with. So we go from a 160 kilodalton antibody down to a 3 kilodalton peptide that we can synthesize and have molecular recognition. So this is what a beta body looks like. The serine residues provide structural stability of the beta hairpin. Beta branched amino acids induce beta structures. And then we have a turn, a proline and a glycine. We have a click bridge that keeps the ends together. And then we have all the residues that can be modified combinatorially for interaction with the protein surface. And this works very well. We can even make 2 of those that recognize each other, as shown here. So we design these 2 to fit together. They are matching topologically, and they are opposing each other with positive and negative charges, hydrogen bonds, etc. And here's the binding curve, and you can see the binding study can be performed directly on beads, where one of the 2 components is fluorescently labeled and the other one is attached to the bead. And there you can see we are down here at 700 nanomolar around, where we have the KD. We can also do this towards protein surfaces which are more stable. So this is the GFP, and you can see a beta body for GFP, and this is interleukin 1 beta, another beta body that interact with that, done by this molecular dynamics it's mutational molecular dynamics, to funnel into the combinatorial beta body that fits best to the surface. And when we make these two, and we have them on the beads, so we have this one on the beads, or we have this one on the beads, and we mix these two beads, so we have two beads here, one with one beta body and one with the other one. And then we add green fluorescent protein, and you can see only one of the beads become green, indicating very selective recognition of GFP. And down here, only interleukin-1 is recognized by this second beta body. And the binding curves shows very nice binding. We can increase that binding by clicking the molecules like I showed before. So this is how we produce very high affinity ligands with GFP, and here with ROX, isoleukin-1 beta. And this one actually is completely selective for interleukin-1 beta, and the protein with exactly the same fold, interleukin-1 alpha, is not recognized at all. So the selectivity is very high for these recognitions. And this is also shown here, where we have mixed a beta body on a bead with a beta body with a fluorophore. Nothing happens, so the beta body is in solution and the other one is on the salt support. They don't interact. But if we add just 20 nanomolar of interleukin-6 towards what this was designed, we get a highly fluorescent bead within a short period of time by the protein diffusing in and binding to one of the two beta bodies and then recruiting the other one from the solution. So that is a very nice and effective sandwich assay for interleukin-6. Again, I'm shifting gear, and this is a project that is concerned with Alzheimer peptides. This is one of our key research areas in the institute. We have here the crystal structure that is most prominent for beta 1 to 42 in fibrils. It was determined by Grima in Science some time ago, and it forms these two stacks of a beta 1 to 42, and they are interacting in this fashion. So what we asked ourselves is that, can we solubilize this fibril? So we would like to take a cross section here and then make beta bodies that interact with the growth phase of this fibril. And that actually was successful. So here is shown two beta bodies. We tried first with one, and then we could reduce the rate of fibrillation. And then we decided we had to make one for each end because the ends are different. And when we did that, we could completely abolish fibrillation here at 37 degrees and here at 25 degrees. So it seems to work, but it wasn't really exactly what we wanted. We can even solubilize fibrils that have already formed, and this is shown here. When we do the peptide addition at this time, we get this curve down here, which is the one that's shown over here. So we weren't really satisfied with the solubility of these compounds. And also we thought that maybe if we included some water shell, we might be able to further solubilize the fibrils. And we made these amino acids, which has the same configuration as threonins, but has 3 extra hydroxyl groups. And we used, so this is glucosaminic acid, we used a silylation technique. First, we added the FMOC group to the amine, and then we used test triflate to introduce a test group, so triethyl silane groups. And after hydrolysis of the carboxylic acid, silyl ester, we then made the building block that we used for the synthesis. And we incorporated these building blocks several times into the beta bodies. And in particular, this beta body 3 and this beta body 5 showed very good properties for our solubilization. So this one up here and this one up here, as you will see, were very efficient in promoting or inhibiting fibrillation. The blue curve here on the top is the fibrillation of A-beta 1 to 42, the 42 amino acid peptide from APP that is released erroneously. This here is what happens if we add peptide 3 and peptide 5. So here at the bottom, you see a turquoise curve, and that's what happens. The same is the case for A-beta 1 to 40, although the molecules were not designed for 1 to 40, but for the crystal structure of 1 to 42, it still has a very dramatic effect on reducing the fibrillation of 1 to 40. So we were very happy with that. And here we have another project on Alzheimer, because we also tried to actually hydrolyze the Alzheimer peptides with catalysts that are metals like palladium bound to carbenes. And we have observed that these could actually be peptide cleaving compounds. So we would like to make an Alzheimer binding peptide, which has a similar structure to the Alzheimer peptides. So it should stack. And then a palladium that is coordinated to a carbene that could then affect the hydrolysis. It worked tremendously. It was really, really nice. We saw a lot of cleavage. The problem was that when we took away the catalyst, it still cleaved. So what happened is that we actually observed some autocatalytic reaction of the Alzheimer peptides, and we decided to investigate this in more detail. So we synthesized a whole range of different compounds from Alzheimer peptides, different fragments and different lengths of Alzheimer peptides. And we started to study this cleavage reaction. It so happens that it happens right in the center of the nucleation site of a beta formation. So this is a really, really important area for the crystallization of the fibrils. So you can see here what happens. We start out with this compound here, and within a short period of time, like 10 days, it starts cleaving. You see F0 here forms, and you see F4 starts to form. You see a little bit of F1, and these are the F0, 1, 2, 3, and 4. And F4 is we end up with F4 and something called F6, which is this part down here in the end of the synthesis. And we can actually measure all of these compounds during the cleavage reaction. So the kinetics is that we have a latency period, and then an autocatalytic reaction starts, and we get the complete hydrolysis of the A-beta peptides. Furthermore, we can do cross-seeding in these experiments. And the cross-seeding is taking some of this active mixture, so mixture at this 13 days, and then we add it to a 1 to 28 or 1 to 40 solution of A-beta. And then you can see the processing starts with little delay. It then starts and it goes to complete hydrolysis. Here we see the seeding in 1 to 40. When there's no seeding, nothing happens. It's quite stable. If we seed with this already starting to hydrolyze a mixture, it forms all of these fragments within a short period of time. And this has a very strong significance. First of all, we plated these solutions of A-beta peptides on mica and did atom force microscopy. And you can see here the formation of these donut-shaped compounds. These are the initial formations of the seeds of the fibrils. At some point, you can see here, down here, a small breakout point. There's another one over here showing some, if I just move this one over here, you can see a donut that is almost completely collapsed. And then you can see, so this is a completely collapsed donut. And then you can see the fibrils are composed of these fragments of donuts that have come together. So that's the procedure for how these fibrils form. And we think that the catalytic activity is in the corners of these donuts. You can see some spots here which are not so tight. So we have these fibril segments that are coming together as donuts, and these autocatalytic aggregates are forming in these areas, probably looking something like this. We are back in Stockholm, and this is on the 10th of December. This is the ceremony. This is the ceremonial dinner. My wife is very proactive, so when she spotted this dress at the Nobel Museum, she immediately called the Institute of Arts at Stockholm University and asked them to actually make one for her as well. And they did within 24 hours. She got this absolutely perfect dress. And you can really see that this is artists that made this dress, because if you look carefully, you can see this is a 6-membered ring and this is a 6-membered ring. And it should, of course, have been 5-membered rings. So when you dress your wife up like this, there's a good chance that somebody spots her. And this is Prince Philip of Sweden. She took my wife away from me. He took my wife away from me, and she was seated between Prince Philip and Prince Daniel, and I was down there in the back somewhere. So that was not so good, but revenge is sweet. And the next day, we got to the castle, and there I got this very prominent position at the table besides Crown Princess Victoria. So everything evens up in the end. Now I would like to go back to the teaching from first grade, or teaching the young people. In my opinion, we should teach them from the first grade in chemistry. And I have a proposal that maybe in a global collaboration, we start actually making animation material which is consistent, and we make 5 minutes every week for first graders, 10 minutes for second graders, and so on. So we build up very slowly a visual understanding of the chemistry universe. So these are very simple videos that actually shows maybe 2 hydrogen atoms that goes together and share the electron density, have some sort of feeling about what is the size of the nuclei compared to the electron cloud, what is the speed of atom movements in different kind of molecules. So we call this AI, and she asks a question and we answer, and we get the video sent to the schools. And then we have a translation unit that can globalize this kind of technology. Because chemistry is everything, and we want to young for chemistry. And I think the positive consequence of that could actually be monumental. It could be environmentally, climatically important, could be politically important. You are better equipped to take the right choices when you have a chemical understanding of reality. And also, it's important for global equality. If we have teaching like this worldwide, we will have much better understanding of chemistry worldwide. So we can share our resources better, we can have a better wealth distribution, and eventually peace in the world. So chemistry early, new curriculums worldwide. Start early, start with visualization and pleasurable learning, and evolve the interest for understanding the scientific world. So because there's a lot of factors that influence the choice of educations. It can be parental influence or institutional influence. It can be courage and identities. It can even be salary, but I think most importantly, it's existential curiosity. So identity building starts very early, and we have to make the right choices for the kids to build the identity that is necessary for choosing these kind of educations. Particular identity by knowledge. So if we teach them knowledge from the beginning, when they start building their identity at the age of 8, 9, 10, we can really overcome some of the parental and authorital beliefs that they have, so that they make the right choice, so that we can actually have our educations match the societal needs and optimize the creation of identity and selection of education, make it efficient education without external pressure, using knowledge and positive reinforcement of self-esteem is inherent in all teaching. So start early and reward good selections. So this is actually about how we fund our research. Today, most research is funded from one big box, which takes care of applied research and fundamental research alike. In my opinion, this should be divided up in two boxes, one which takes care of fundamental research and one which takes care of applied research. And these should be completely independently created and evaluated. So we can have our disruptive novel research that secure the future in competition and also can optimize known knowledge for applications. So with that, I would like to thank all the people who have been involved in developing the click chemistry. They are all listed here. They have all been involved in one way or another in developing this over the last 20 years. And I would also like to thank my family for being patient when I went to work in the weekends or even on holidays in order to make these results come true. And thank you for your attention.
Thank you very much for our wonderful talk, Professor MELDAL. I'm sure that every audience is inspired by the very fantastic aspect, starting from the interactive item and then the state-of-the-art research result of you about the peptide chemistry and then the teaching. Thank you very much. And I'd like to take several questions from the audiences from now. Please come in front of the microphones if you have questions.
Thank you for lecture. So I'm interested in the QAC reaction. So which stage kappa is critical to decrease the energy of activation barrier?
Yeah, so the copper, first of all, the copper has a very high affinity for the alkyne. And it actually decreases the reaction in two ways. It interacts with both the alkyne and the A side, making the proximity very close between the two reacting partners. So that's one of the reasons. The other reason is that it's actually reducing the barrier of reaction so that you have an acceleration of the reaction with 10 to the 7th. Because the reaction can also occur if you boil alkynes and acids. They will react in an unspecific manner to form the 1,4 and the 1,5 compounds. But this is not useful in the presence of proteins that would denature and so on. So the catalysis with copper is essential for making these kind of reactions.
Okay, thank you.
Thank you. Thank you for your lecture. I'm Mai Kikumoto, a neurologist from Hiroshima University. So I'd like to know whether amyloid beta hydrolysis and cross-seeding of catalytic activity can be seen when amyloid beta is located on the cell membranes, because they are originally localized on the cell membranes, on neurons.
Yes. So yes, they can actually. If you are looking at the neurons in the vicinity of the plaques, you will find fragments of NCAM2, which is the protein that glue together the neurons and make tight junction between the neurons. And these are fragmented by something in the plaques, and we are very sure that is probably the proteolytic activity of the beta peptides that you see there. You also find the fragments. In 2016, it was published that you found fragments of a beta which are not explained by any of the enzymes activities that are your natural enzyme activities that are included.
Thank you. So is there any difference between the reactions with amyloid beta on the membranes of neurons and the plaque of amyloid beta plaque?
Yeah, I think that well, I don't know, but you probably have to have this formation of the donuts of the structure that is actually responsible for the fibrils and the plaque formation. You probably need that kind of structure to get the peptides interacting in the proper way. You can see there's a long lag period before you get this enzyme activity. And this lag period is significantly longer for a beta 1 to 40. I think probably about half a year. And this is probably why you have initially plaques, but no dementia, no neuronal death. And then later on, you have significant amounts of neuronal death and dementia development.
Thank you. Thank you for answers.
Hi, I'm Meng Lan from Singapore. So it seems that you can use click chemistry to join proteins together. So is it possible to use this design to make complexes of proteins that may not naturally complex together? And is there any rules that we can follow in deciding whether these two proteins can be joined by the click chemistry?
Of course, if you have an active site of a protein that you want to utilize, you should not pick anything in the vicinity of that active site. So usually I would go from some ends sticking out and combine the functionality in a way that they will actually, not hinder each other's function. So that could be at the end terminal, where if you have a hexahistidine expression of a protein, then you also have the possibility to use that hexahistidine as a catalyst for acylation. You can install an A site at the end terminal almost selectively. This is a paper published by Knud Jensen here from Copenhagen University last year. And that can then be used for attachment of an alkyne in another protein, which you can install by this amber stop codon technology. So there's many different ways to look at insertion of the functional groups that is required for the click reaction.
Thank you.
Yeah. Hi, Professor. I'm Hwa-Pyong Kim from Republic of Korea. My question is, what is the key properties making kappa-1 good catalyst for click chemistry?
So I don't know exactly what the property is, other than that it really strongly coordinates to the alkyne, more so than any of the other atoms in the periodic table. And you can actually use silver 1 or gold 1 as a catalyst for this reaction, but not as a catalyst, but as a reagent for this reaction. But the gold and the silver does not leave the triazole. It's strongly bound to the triazole and it won't leave it, so it cannot be used as a catalyst. And we have tried all the different metals around the copper, and nothing else works as well as copper.
Thank you.
Okay, so time is now over. So I believe the future Nobel laureate will appear among the audiences here. So I'd like to close the Q&A session now. So please join me in thanking Professor MELDAL for the wonderful lecture.
Thank you very much, Dr. MELDAL and Dr. Oisaki. Let us show
Thank
our
you.
appreciation with a round of applause. Oh, sorry. Thank you.